So this is question 15 from section C on the combined gas laws. So it says a toy balloon has an internal pressure of 1.05 atm and a volume of 5 liters. If the temperature where the balloon is released is 20 degrees Celsius, what will happen to the volume when the balloon rises to an altitude where the pressure is 0.65 atm and the temperature is negative 15 degrees Celsius? So at first this question seems to have a lot going on. It's got a lot of different moving variables and literally a balloon moving through the air. So we know that we're going to be working with the combined gas law. So P2V2 over T2. And it has all of those variables. It has pressure, it has volume, and it has temperature. So we're going to be utilizing all 6 of those variables. So let's go ahead and find all those variables. So a toy balloon has an internal pressure. So the pressure, initial pressure, is 1.05 atms and a volume of 5.0 liters. If the temperature where the balloon is released, so we're going to go ahead and assume that that's the initial temperature, is 20 degrees Celsius. What will happen to the volume when the balloon rises? So our volume, our secondary or final volumes are unknown. The pressure goes down to 0.65 atm. And the temperature also goes down to negative 15 degrees Celsius. So we have all our variables just from that problem. A couple things to make sure of. We have to, first things first, convert to Kelvin. So let's go ahead and convert our initial and our final temperature to Kelvin. So by adding 273.15, so 20 plus 273.15. So for T1, we get 293.15 Kelvin. For T2, we do negative 15 plus 273.15. We get 258.15 Kelvin. The other important thing with our combined gas laws is that they have to match. Those units have to match from beginning to end, initial to final. So let's check it before we plug in. So P1 and P2 are both atm. V1 is liters, which means V2 will come out as liters. T1 and T2 are both Kelvin. So that means we're good to go. Let's go ahead and plug it all in. So P1, 1.05 atm. Our volume is 5.0 liters. T1 is, make sure you plug in that Kelvin, 293.15 Kelvin. P2, our final pressure, is 0.65 atm. Our V2 is our unknown. We're trying to find that volume. Then that T2 is 258.15 Kelvin. So you can either go about this 2 ways. You can go ahead and solve the side that doesn't have the variable, or you can cross multiply from the get-go so that you don't have those fractions anymore. So what I'm going to do is I'm going to go ahead and solve that left-hand side. Since there aren't any variables, we can go ahead and just plug in all those numbers and solve for it. So we'll say 1.05 times 5 divided by 293.15. You get a tiny number. It is 0.017. Let's go all the way out to 9. And then all those units, atm times liter per Kelvin equals, let's go ahead and rewrite that right-hand side. We didn't do anything with it, so we'll keep all of that information the same. Just pull it on down. We want to get that temperature out from under the denominator, so we're going to go ahead and multiply both sides by 258.15 so that we can get rid of that. Times 258.15. So now our new left-hand side is 4.623. Those Kelvins cancel, so it's atm times liter equals 0.65 atm V2. Again, we're trying to isolate that secondary volume, so let's divide both sides by 0.65 atms. It cancels on the one side, so V2 is by itself. Our units cancel over on the left-hand side, so liters is all by itself. So we're going to do that divided by 0.65. And we get our new and final volume to be 7.11 liters. So if you follow through those units all the way, you'll see that liters is the only unit left. So that is what our answer is going to be in. Awesome.